Second part of section 10.1, we're going to look some more at tangents and properties of tangents. And the first thing we're going to do is a little discovery. I'm going to draw the line from the center of the circle to the point of tangency. And if you think about any line from the center of a circle to a point on the circle, that's a radius, right? And my question is, what angle do these lines appear to meet at? What angle does it look like the radius meets that tangent line? I know it's a tangent line because it hits at only one point. And I hope that you're looking at these thinking, it looks like a right angle. It looks like it meets at 90 degrees or that it's perpendicular. And it is true that anytime you have a tangent line and you draw the radius to the point of tangency, they are perpendicular. So this theorem says a line is tangent to a circle if and only if, remember that works both ways. So this line is tangent if and only if it is perpendicular to the radius drawn to the point of tangency, meaning that that would have to be a right angle. So it's kind of neat. It's a way to check if you have a tangent line, if it's perpendicular to the radius drawn to this potential point of tangency, and you know that it's true. If you have a tangent line, you can draw the radius and know it's a right angle. And I'm going to prove that to you in Geometry Sketchpad here. I have a circle. The center is at C, B is a point of tangency, and this line AB is a tangent line. And you notice measure of angle ABC, which is at angle B, is 90 degrees. And no matter what, watch the 90 degrees, it'll never change. If I grab that circle, I'm changing the size of the circle, I'm changing where it is, but no matter what, this is staying 90 degrees. Because a tangent line is always perpendicular to the radius drawn to that point of tangency. And we're going to use that fact as we do some examples here. So one thing we can do is determine whether a line is tangent to a circle or not. It says in the diagram, line segment AB is a radius of circle A. Okay, A is the center then if it's called circle A, and AB is a radius. Is BC tangent to circle A? BC is this line. It looks like it might be tangent, but maybe it hits at 2 points. It might not quite be a tangent line. Maybe this is going through that circle. So how am I going to know if it's tangent? Basically, you're thinking, I need to know if angle B is a right angle. So I need to know if angle B is a right angle. Because if it is, then this thing is definitely a tangent line, right? If that is a right angle where the radius meets the point of tangency, the maybe point of tangency, I should say, then it would be a tangent line. But how am I going to check if this is a right angle? Basically, test if you have a right triangle. Back in chapter 7, we used Pythagorean theorem and the converse of the Pythagorean theorem to determine whether we have a right triangle. I know this radius is a length of 25. This line that might be a tangent is 60. And this segment from the center to the point outside the circle is 67. So I know this would potentially be the hypotenuse if this is a right angle. These would be the potential legs. So let's test it. Remember, you do the longest side squared, which here would be 67 squared. This would be our hypotenuse, maybe. Is this equal to one leg squared plus the other leg squared? Again, I don't actually know if these are legs. I'm checking it out. Now, if these are equal, it's a right triangle. Therefore, this is a right angle. Therefore, it is tangent. If this is not a right triangle, this is not a right angle. Therefore, it's not tangent. Let's see what happens. In the calculator, 67 squared is 4489. And in one step, I'm going to do 25 squared plus 60 squared on the calculator. Uh-oh. I get 4225. And I'm saying uh-oh because these are not equal. This is not a right triangle. Therefore, that's not a right angle. Not a right angle. Therefore, is this line tangent? No. Because it's not a right angle here, it's not a right triangle, and therefore it's not tangent. It must mean it actually hits at 2 points and kind of goes through that circle. So even though it looks close, it was not a tangent, but this is a way to test. Okay, that radius would have to form a right angle to that point of tangency. So kind of cool that we have this foolproof method now. This here is actually probably one of the toughest examples today. It says in the diagram S is the point of tangency. If S is a point of tangency, then this line segment is a tangent line. I want to find the radius, they're labeling it R, of circle T. Now why do they have R in two places? Well, isn't this a radius here, and this is a radius here, and you know every radius is the same length. How am I going to find the radius? Well, wait a second. If S is the point of tangency, well, I didn't mean to draw over that. If S is a point of tangency, then I know that this is what kind of angle? I know it's a right angle, therefore I have a right triangle, and I can use Pythagorean theorem to try to find that radius. Now this is going to take some work, because if you think about it, the hypotenuse here is this entire length. What would you do with R and 36 to get the entire line segment? Well, you'd add them, right? If you knew this was 10, you would do 10 plus 36 to get the whole segment. So my hypotenuse is going to be R plus 36. And then R and 48 are my legs. So if I do one leg squared, R squared, plus the other leg, 48 squared, that should equal the hypotenuse, R plus 36 squared. This is where I have to be real careful. First of all, I'm not just squaring 36, I'm squaring an entire quantity. And second of all, if I'm squaring that entire quantity, R plus 36, these things are being added. I cannot just distribute that squared in. With that addition, you can't bring in the squared. That only works with multiplication. R plus 36 squared means literally, what does it mean to square something? Multiply it by itself. R plus 36 means R plus 36 times R plus 36. That's what it means to square something, is multiply by itself, which then will require me to distribute 4 times. Okay, so be careful. The fact that you're adding, you have to multiply it by itself and get 4 terms here. I still have my R squared plus, actually I might as well do 48 squared. I get 2,304. R times R is R squared. R times 36, 36R, and I get another 36R there. 36 times 36 is 1296. Sorry, I'm running out of room there. And on this side I should combine like terms. I have R squared plus 2,304 equals R squared plus 72R, right? That would be 36 times 2. And then plus my 1,296. Something works out very nicely here. I have R squared on both sides. If I subtracted R squared, it would go away from both sides. So this becomes a lot easier than it appeared at first. No more quadratic. I just have 2,304 equals 72R plus 1,296. Get R alone. So I'm going to subtract 1,296 from 2,304. Took me a second on the calculator there. I got 1,008 equals 72R divided by 72. And I figured out that the radius is 14. So it took some work there. I had to be real careful with the hypotenuse there. Doing a lot of distributing and come up with a radius of 14. And that looks reasonable. If this had been 14 plus 36 giving me 50. And I can check in the calculator 14 squared, which is one leg squared, plus the other leg squared, 48 squared. That equals 2,500, which is what 50 squared equals. So we're good to go. Alright, another theorem. We're talking about common tangents from one external point. This theorem says tangent segments from a common external point are congruent. So, tangent segments, meaning more than one tangent segment from this common external point. I have a point out here, it's external because it's outside the circle, and I'm going to do tangent segments. So you think about it, I can do one tangent segment above or to this right side of the triangle, and of the circle. I can do another tangent to the bottom side of the circle. Both tangent because they both intersect at just one point. And the cool thing about these segments, they are congruent. There's only 2 tangent segments you can do from any external point, and they do have to be congruent. I'll prove that to you in Geometry Sketchpad here. I have a circle, centers at C. D and B are both points of tangent C, because EB is a tangent and ED is a tangent. If you notice, I did the length of D and B, both 4.05. I can change the size of this circle, and you watch these numbers, they'll always be the same. I can change the size of the circle, where that point E is, but they always change together. Those two tangent segments from that one external point are always the same length. They're always congruent. And let's do some examples with that. In circle C, DA is tangent at point A, and DB is tangent at point B. Find X. Well, what do I know here? I got two tangents, then, to the same circle. They are congruent. I know that 25 is congruent to 6x minus 8. If those are congruent, I should be able to set them equal and find out what x is, because this 6x minus 8 should be 25 as well. Get x alone, I'm going to add 8 to both sides. 25 plus 8 giving me 33. And then I have to divide by 6. And x equals 5.5. Alright, what about in this one? Find x. Oh, this should be marked. This is the center of the circle. If you notice, I have right angles here and here. Well, what does that mean? These are radii drawn to a point of tangency then, because of the fact that the radius meets this at a right angle. These are tangent lines. And what do you know about two tangent lines from the same external point? They are congruent. So right now I know that x squared should be equal to or the same as 64. Those should be the same length. And to solve for x here, this is x squared, so I take the square root, and the square root of 64 is 8. So two tangent segments from that common external point are congruent. Another example, kind of going back to our first theorem today, is line DE tangent to circle C. Okay, well, it's only tangent if this is a right angle. Right? Because every point of tangency meets at a right angle with a line with a radius drawn to that point of tangency. This needs to be a right angle, because I need this DE. If it is a tangent line, it needs to be perpendicular to that radius drawn to that point of tangency. Now, to see if that's a right angle, I have to test if it's a right triangle. Then I would know if it's a right angle or not. Test if this is a right triangle. So I'm doing converse of the Pythagorean theorem. Oh, I'm missing something. Do I know this length here? I know this part is 2, this is 4, this is 3. What's this length? Well, wait a second. CE is a radius. And isn't this just another radius? So this would also have to be 3. And when I need this entire side, this side is 3 plus 2, or 5. Now, is this a right triangle? One leg is 3, maybe leg, because we don't know if it's a right angle. The other maybe leg is 4. So 3 squared plus 4 squared, we're testing, is that equal to the potential hypotenuse of 5 squared? Actually, maybe you remember this. This is our most common Pythagorean triple 3, 4, 5. This does work. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, and of course 5 squared is also 25. So is DE tangent to circle C? Yes, because this is a right triangle. Check. Therefore, if it's a right triangle, this is a right angle. Check. If this is a right angle, DE is tangent to circle C because the radius drawn to that point of tangency, point E, is a right angle. Okay, so testing again whether you have a tangent line based on the fact whether a radius drawn to that point of tangency is a right angle. And I have one more example. Find the radius in this problem. Now, we did an example just like this one, where the radius is labeled twice because it's drawn twice. We know we have a tangent line in this length of 24 because it meets at a right angle with this radius. I need you to find that radius. You're going to use Pythagorean theorem. Be careful when you come up with an expression for this entire length. You're going to do leg squared plus leg squared equals whatever you get for the hypotenuse squared. And I want you to come in class tomorrow with this done, and we'll discuss it.